Wait, did you hear that? I could have swore the wall made a sound. Well, maybe I'm just hearing stuff in my head. But a scientist once told me that all atomic matter creates sound. So I know it's making a sound. But we can't hear all the sounds that the world makes because it's below the minimum threshold of our hearing. Fortunately, we have a branch of psychology known as psychoacoustics to help us examine what makes different sounds sound different. Psychoacoustics is a scientific study of sound perception. Hearing and processing sound are phenomena relevant to everyone listening to this video. And an appropriate understanding of these mechanisms will enable us to develop technology for those who are either listening enabled or even the listening impaired. So let's discuss some of the fundamentals of psychoacoustics. We'll begin by looking at the basics of sound production, followed by talking about the human auditory system's reception of sound, and then look at a few interesting aspects of subjective sound perception. So let's begin. Sound is produced from the vibrations of particles. Now, as a particle vibrates, it produces variations in pressure that transmit across a channel from the interaction of particles next to each other. Now, this transmission of energy in the sound sense is a transmission of acoustic energy, which we commonly refer to as a sound wave. Now, for this particular speech, the channel by which you can hear me talk is the air, unless you are listening to this underwater in a pool, which you should probably stop. Now, as the speakers or the headphones that you're using to listen to this speech produce sound, the sound travels through the air toward your peripheral auditory system, which is a fancy word that just means the outer, middle, and inner parts of your ear. Now, according to Yi-Ching Lin in her 2015 book, Audio Watermark, it is a series of functional parts working together that enables us to receive and process sound. Now, if we take a look at the screen, we can examine a little bit closely these individual parts and their sequential role in the reception of sound. Initially, sound passes into the ear through the auditory canal and travels to the middle section of the ear, which the first instance is the eardrum. Now, the eardrum vibrates in accordance to those variations in pressure produced by the sound incident upon it. It sends the signal through a series of bones known as the ossicles, which culminate in the oval window. And that oval window is an interface to the cochlea, which is the spiral-looking thing. Now, as the oval window moves, the fluid that is inside the cochlea moves in accordance to that motion and passes over the floor inside the cochlea of a membrane called the basilar membrane. This basilar membrane contains a number of hair cells that, as the fluid passes over it, are stimulated and send neural impulses to the brain where the sound is actually perceived. So that describes how sound is heard, or rather sound is received. But how do we talk about our subjective perceptions of sound? Well, that is really a result of the different physical properties of the sound producer. So, to begin with, when a particle vibrates rapidly, producing rapid variations in air pressure, the frequency associated with that motion is higher, and the pitch that we perceive is higher, like this. Likewise, when the rate of motion of that variation in pressure is slower, the frequency associated with that motion is lower, and the pitch we perceive is lower, like this. Now, a sound producer does not generally exhibit only a single frequency, but rather a set of frequencies that are related to each other. The base frequency in this set is known as the fundamental, and all the frequencies generated above this fundamental value are usually integer multiples of the fundamental frequency value. This is easiest to demonstrate with a musical instrument. So I've brought my acoustic guitar to show you. Now, the acoustic guitar string, its physical properties, the length, the thickness, and the tension, all are influencing the actual sound that is produced when I pluck the string. Now, we perceive a certain pitch associated with that sound, and that pitch is directly related to the fundamental frequency occurring in that sound. Now, however, that fundamental frequency is not the only frequency occurring in that sound. Rather, any wavelength that can fit as a combination of itself within this length of string will actually exhibit some presence in the sound that is produced. Now, I can try to isolate some of these particular frequencies by placing my finger at a node halfway between the endpoints of the string. This forces only the wavelengths whose have a node halfway between the endpoints of the string to be present. Now when I play the string, we perceive a higher pitch. Now, herein lies the mystery of why different musical instruments playing the same pitch sound different. Two different musical instruments can be playing the same pitch, and they could have the same set of frequencies, all the same harmonics, but they still sound different. The reason is because of the relative amplitudes of the harmonics in relation to the fundamental. A certain musical instrument, say a guitar, may exhibit a dominance of particular harmonics above that fundamental frequency, whereas another instrument playing the same pitch, say a piano, will present a different dominance of different harmonics above that fundamental frequency. And thus we perceive different types of sound or different musical timbres. Now this leads to the next perceptive discussion that I'd like to talk about, which is loudness. Loudness is related to the energy present in the vibrations of a particle producing sound. Now, loudness is not only dependent on the amplitude of the wave that is the source of the sound. Research has shown that our perception of the loudness of a sound is also dependent on the frequency of that sound. Now, two scientists named Harvey Fletcher and Willard Munson first discussed this in 1933 in their paper, Loudness, Its Characteristics, Definition, and Perception. They developed a set of curves known as equal loudness contours, which I will show an example of on the screen. Each of these curves, when viewed in isolation, represent the relationship between frequency and sound pressure level for a particular tone to be perceived with equal loudness. For example, if we look at this third curve, where this 30 is, a 1,000 hertz tone at 30 decibels, which is a unit of sound pressure level, will be perceived equally as loud as a 40 hertz tone with sound pressure level of roughly 65 decibels. Now, 30 decibels is like sitting in a library environment, whereas 65 decibels is like having a conversation in a loud restaurant. So there is a significant difference in those sound levels. This may describe one of the tendencies for us in our musical listening preferences. You may have noticed that a certain number of people enjoy turning up the bass on their music. Well, in order for us to perceive the same amount of loudness between a lower frequency and a higher frequency, we need a larger level in the lower frequency end in order to perceive that same loudness, and thus we boost the low end. Well, there is a basic summary of some of the fundamentals of psychoacoustics. We looked at the production of sound, followed by talking about the human auditory system and its reception of sound, and ended by discussing some of the basic perceptual characteristics of sound that are subjective. Now, all this discussion will relate the physical properties of sound to its subjective perception. And this is just simply the beginning of this overall field of psychology. So I hope with this information in mind, you can now apply this in your everyday situations, your conversations, the music you listen to, and you can be aware of these different human tendencies and the actual physical properties of the sound that is producing the sound that you listen to. So I thank you for your time, and I hope you have a good rest of your day.